This topic is finding the limit of a ratio of algebraic functions at a removable discontinuity. So again, we're still trying to evaluate limits. One way we learned was using a table. Another way we learned was graphically. A third way that we have to be able to do it is algebraically. So how do we solve this algebraically? By hand. If you go back to the notes for evaluating limits algebraically, remember if it's a polynomial, rational, or radical function, the first thing that we want to do is always try plugging in the number. If you get a valid number, that is the limit. But what you're going to realize in these examples is we're going to be in this case. We're going to get 0 in the numerator and 0 in the denominator. And when that happens, that is called indeterminate form. Because we're dividing by 0, that means the function's undefined at that point. But remember, with limits, it doesn't matter what happens at that point, it's what happens near that point. So just because we get 0 over 0, which is undefined, does not mean that the limit is undefined. So we are going to have to do a different technique. Two tricks that I wrote up in the notes for you about solving limits when you have that 0 over 0 in determinate form. There's one tip for when you have a rational function and a different tip when you have radical functions. When you have rational functions, the first thing is it a compound fraction? And a compound fraction would be something like this, where you have a fraction over a fraction. The idea would be to eliminate the compound fraction by getting common denominators in the numerators or multiplying everything by the least common denominator. So you want a single fraction, not a compound fraction. When you do have a single fraction, you're going to try to factor and simplify, and then you're going to plug the limit into the simplified version first. So simplify common factors, and then try directly plugging it in. So with fractions, clean up the fraction to make it a single fraction, factor, and simplify. When you have radicals, what you're going to do is multiply by a conjugate. And this comes from something like this. When you had a radical in the denominator with trig, 1 over the square root of 2, for instance, you would multiply by the square root of 2 over the square root of 2, which would give you the root 2 over 2. So this was called rationalizing the denominator. Well, it got a little more complicated when you had something like this. 1 over x plus the square root of 2. You would have to multiply both the numerator and denominator by the conjugate. And remember, a conjugate, if you have a positive, the conjugate is the negative. So that'd be like x minus the square root of 2. And if you do it in the denominator, you also have to do the same thing in the numerator. So you would multiply it by the conjugate in both the numerator and the denominator. That would eliminate your radicals, okay, at least in the denominator. So that's going to be our trick anytime we have a radical function, is we're going to multiply by the conjugate. So let's go ahead and get to some examples working through this. These are more difficult examples, so please follow along carefully. The first one says find the following limit. The limit is x approaches 16 of the fraction. In the numerator we have the square root of x minus 4. In the denominator we have x minus 16. Again, what we always want to try first is just direct substitution. So let's try plugging it in. We'd have the square root of 16 minus 4 in the numerator, and then we'd have 16 minus 16 in the denominator. The square root of 16 is 4, so 4 minus 4 is 0 in the numerator. And 16 minus 16 is 0, so again, this is indeterminate form. It is undefined at that point, but just because it's undefined at that point does not mean the limit does not exist. So we're going to try to do some algebraic manipulation to be able to simplify this function and then reevaluate this function in the simplified version. So let's do some of that algebra manipulation now. Let's look at the original function, the square root of x minus 4 over x minus 16. Notice this is a fraction with a radical, and we already said when we have a radical, the trick is going to be multiplying the numerator and denominator times the conjugate. So in this case, we have the square root of x minus 4. The conjugate of that would be the square root of x plus 4. Again, it's the exact same thing. All you're doing is changing the sign. If I multiply the numerator by the square root of x plus 4, then I need to multiply the denominator by the square root of x plus 4. Here's a big tip for you. Multiply out or FOIL out the numerator. Do not FOIL out the denominator. So I'm going to keep my denominator exactly the same. I'm going to have one factor, that's x minus 16. My second factor is going to be the square root of x plus 4. In the numerator, I do want to FOIL. So let's go ahead and FOIL it out. The first term would be the square root of x times the square root of x, which is x. The second term, the outers, would be plus 4 times the square root of x. We look at those inners. I'm going to have minus 4 times the square root of x. And then I look at those last terms. Be careful with your sign here. Minus 4 times a positive 4 would be minus 16. Notice in the numerator we have a positive 4 root x and a minus 4 root x, so those two terms actually cancel out to be 0. What's left in top would be x minus 16. On bottom, one factor is an x minus 16, and another factor is the square root of x plus 4. Notice, though, now in the numerator and the denominator, we have a factor of x minus 16, so those two factors simplify into a 1. So simplifying this further, we would have a 1 in the numerator and then a square root of x plus 4 in the denominator. So these two functions are mathematically equivalent except for at the point x equals 16. Again, we don't care what happens at that point, we only care what happens near the point. So with the limit, instead of plugging the limit into the nasty original function, we're actually going to plug the limit into the nicer simplified function. So what we're saying then is this is equivalent to the limit as x approaches 16. Again, instead of plugging it into the original function, we're going to plug it into the simplified function, the square root of x plus 4. We're going to try the direct evaluation method just by plugging in the number. So this would be 1 over the square root of 16 plus 4, which would be 1/8. So that should be our final answer there of 1/8. So remember, originally when we plugged it in, we got that the function is not defined at that point. That doesn't matter. We could still find the limit. We multiplied by the conjugate. We simplified. Then we evaluated the limit into the simplified version and got 1/8. That's our final answer. Let's try it again on another example. Example 2 says find the following limit. The limit as x approaches 1 of the quantity. In the numerator we have x minus 1. In the denominator we have 5 minus the square root of 26 minus x. Always try direct substitution first. So let's try plugging in the number 1. In the numerator we'd have 1 minus 1. In the denominator we'd have 5 minus the square root of 26 minus 1. Square root of 26 minus 1, well 26 minus 1 is 25. The square root of 25 is 5. And 5 minus 5 is 0. So in the denominator we have 0, in the numerator we have 0, so that's indeterminate form. Again, all that means is my function is not defined at that point. That does not mean the limit does not exist. So to see if the limit exists, we need to use one of our tricks or techniques to simplify the function. I'm going to look at that original function. I have x minus 1 in the numerator. I have 5 minus the square root of 26 minus x in the denominator. I'm going to multiply by the conjugate here. And in this case, I'm going to multiply by the conjugate of the denominator. The conjugate of the denominator is 5 plus the square root of 26 minus x. Again, the only thing I do is change that minus to a plus. If I multiply the denominator by that quantity, I have to multiply the numerator by that quantity as well. So there's my 5 plus 26 minus x. Again, the trick is do not FOIL out the numerator here. All you want to do is FOIL out the denominator. So in the numerator, my first factor is an x minus 1. My second factor is a 5 plus the square root of 26 minus x. In the denominator now, I'm going to actually FOIL it out. So for the first terms, I do 5 times 5, that's 25. I do the outers. I would have plus 5 times the square root of 26 minus x. I do the inners. I'd have minus 5 times the square root of 26 minus x. And then I do my last, let's be really careful with this. A negative times a positive is a negative, so this is going to be subtraction here. And then I have the square root of 26 minus x times the square root of 26 minus x. Make sure you use parentheses here. You just get 26 minus x. Really important you use parentheses here because we are going to have to distribute that negative to both terms. So let's clean up that denominator. Notice we have a positive 5 square root 26 minus x and a minus 5 26 times the square root of 26 minus x. So those cancel and become a 0. And then again, we do need to distribute that negative through to both terms. So in the numerator, I'm going to have one factor of x minus 1, another factor of 5 plus the square root of 26 minus x. In the denominator, I have that 25. Then I'm going to go ahead and distribute that negative, so it would be a minus 26, and then subtracting a negative x actually turns into a plus x. I'm going to clean this up just one more step. In the numerator, I have that factor x minus 1. I have that 5 plus the square root of 26 minus x. And in the numerator, I'm going to write it in descending order, so my x goes first, and then 25 minus 26 is a minus 1. Now notice, in the numerator, I have a factor of x minus 1. In the denominator, I have a factor of x minus 1. So those factors simplify to be 1s, and I'm left only with the function 5 plus the square root of 26 minus x. So if I look at my original function, and I look at the now simplified version when I multiplied by the conjugate, what we're saying is, yes, these functions are identical everywhere except at the point x equals 1, but again, for limits, it doesn't matter what happens at the point, it's only what happens near the point. So finding the limit of the original function is the exact same thing as finding the limit of the simplified function. Again, that simplified function was the square root of 26 minus x. Coming in with the simplified version, I'm going to try the direct substitution method. I'm just going to plug in the number 1, so that would be 5 plus the square root of 26 minus 1. 26 minus 1 is 25. The square root of 25 is 5, and 5 plus 5 would be 10. So our answer here should be 10. So again, both of these examples, when I did this, both of these examples had radicals. The trick was multiplying by the conjugate. Only distribute the numerator or denominator that has the radical. Leave the other one exactly as it is because it will simplify. Then instead of evaluating the limit at the original difficult function, you actually want to evaluate the limit at the more simple function. Okay. Let's try some examples that are just fractions. In fact, these are going to be compound fractions, meaning we have fractions in the numerator and the denominator. The next limit is the limit as t approaches 4 of a fraction, and in the numerator we have 1/4 minus 1 over t, and then in the denominator we simply have t minus 4. Again, I'll always try direct substitution first, so this would be 1/4 minus 1 over 4. And in the denominator, we would have 4 minus 4. Notice in the numerator, when we simplify, we would have 0. In the denominator, we would have 0, which is indeterminate form. Again, indeterminate form means the function does not exist at that point, but that does not mean the limit does not exist at that point. So we're going to have to algebraically manipulate this function, simplify it, and then plug it into the simplified version of the function instead. Let's take a look at that function. 1/4 minus 1 over t, and all of that is over t minus 4. This is called a compound fraction, where we have fractions over fractions. The easiest way to get rid of compound fractions is to multiply every single thing times the least common denominator of all terms. So where do you see denominators? I see a 4 and I see a t. Those are the only two denominators here in the compound fractions, so the least common denominator between those would be 4t. So the idea is I'm going to multiply the numerator by 4t, and I'm going to multiply the denominator by 4t. So again, all I'm doing is multiplying by the number 1. I'm going to distribute in the numerator. I am not going to distribute in the denominator. So in the numerator, I'd have 4t times 1/4 minus 4t times 1 over t. In the denominator, I'm just going to leave it as 4t times t minus 4. I'm going to leave that as 2 factors. Notice in the first factor, 4t times 1/4, the 4's simplify. And in the second fraction, the 4t times 1 over t the t's simplify. So when I do that, it looks to me like I'm getting t times 1 on the first term, which is t, 4 times 1 on the second term, so that'd be minus 4, and then in the denominator I have 4t times t minus 4. Notice in the numerator I have a factor of t minus 4, and in the denominator I have a factor of t minus 4, so those two factors are going to simplify. When I simplify that, I have a 1 in the numerator and I have a 4t in the denominator. So this complicated, complex fraction actually simplifies to the simple fraction 1 over 4t. Because this is a limit, we know that the function doesn't exist at 4. We care about what happens near 4. Instead of finding the limit of t as it approaches 4 of that original difficult function, we are actually able to plug it into the simplified function as well instead. So this is the exact same thing as finding the limit as t approaches 4 of 1 over 4t. We're going to try the direct substitution method. Wherever we see a t, we plug in a 4. So I'm getting 1 over 4 times 4, which would be 1/16. Because I got a number, that is my answer of 1/16. Okay, clean that up a little bit. And there we are. Let's go to the last problem here. This is the limit as y approaches 3 of y minus 3 all over 1 over 7 minus y minus 1 over 4. Again, we're always going to try direct substitution first. So anywhere I see a y, I'm going to plug in 3. So this would be 3 minus 3 in the numerator. It'd be 1 over 7 minus 3 in my first fraction in the denominator minus 1/4. 3 minus 3 is 0. 1 over 7 minus 3, well 7 minus 3 is 4, so that'd be 1/4 minus 1/4, which is also 0, so that gives me that indeterminate form. Again, that just indicates that my function does not exist at that point. It does not indicate that the limit does not exist, so we need to do algebraic manipulation to simplify this compound fraction. Once it's simplified, we're going to plug the limit into the simplified version instead of this complicated version. So let's look at that function, that y minus 3 all over 1 over 7 minus y minus 1 over 4. Nasty looking compound fraction. Again, we have fractions over fractions. What's the way of taking care of that? The way of taking care of it is by looking at any term that has a denominator. So one of the denominators is 7 minus y, one of the denominators is 4. So that least common denominator that we have is going to be both of those factors. It's going to be a 4 and a 7 minus y. So I'm going to multiply everything times a 4 and a 7 minus y. Okay? What would happen? In the numerator, I am not going to distribute at all. I have a 4, I have one factor of 7 minus y, I have another factor of y minus 3. But in the denominator, I'm going to distribute that 4 and 7 minus y to both of the terms. So there's going to be a 4, a 7 minus y, and that's times the first term, which was 1 over 7 minus y. In my second term, I'm going to have minus 4, a 7 minus y, and then the term was a 1/4. Notice in that first term, the 7 minus y factors simplify, and in the second term, the 4's simplify. Okay? I'm going to be really careful here. In the numerator, I have a factor of 4, a factor of 7 minus y, and I have a factor of y minus 3. I totally wrote that wrong. Right here, that was a y minus 3, correct? Okay. And then in the denominator, in that first term, the 7 minus y simplified, so I just have a 4 left. In the second term, the 4 simplified, so I have subtracting that 7 minus y, but I need to be really careful here. I have to distribute that negative to both of those terms. So I have to subtract the 7, that would be a minus 7, and then I have to subtract a negative y, which actually turns into a plus y. Let's try cleaning that up a little bit. When I clean that up, in the top I have that 4. I still have the factor of 7 minus y, and I still have that y minus 3 factor. In the denominator, if I write it in descending order, I'd have my y first, and then I have that 4 minus 7. 4 minus 7 is a minus 3. Well, now we could even keep on going from here, because I have a factor of y minus 3 in the numerator and y minus 3 in the denominator, so those simplify to be a 1. So it looks like I'm left with 4 times 7 minus y. So that original nasty compound fraction simplified into 4 times 7 minus y. So what do? Instead of evaluating the limit at that original nasty looking function, I'm going to be evaluating the limit of that nice function instead. So we know this is equivalent to the limit as y approaches 3 of the new nice simplified function, 4 times 7 minus y. When I look at that, I'm going to try direct substitution. I'm going to have 4 times 7 minus that y value was a 3. This is going to be 4 times 4, which is 16. And that would be my answer. As I evaluate it, if I'm able to get a number, that number is the answer. So both of these problems, compound fractions, looked really nasty. We're doing the algebra that we reviewed in the algebra packets, where we simplified a compound fraction by multiplying every term by the LCD. Once you have that simplified version, instead of finding the limit of the nasty version, you plug it into the simplified version and you're able to get your answers. So there it is. There's our topic of finding a limit of a ratio of algebraic functions at a removable discontinuity. I hope that helps.